Hello everyone, welcome to my presentation. Today I'm going to be talking about password hashing, and this is part one of a two-part series. Today I'm going to talk about cracking the shadows, or in other words, cracking the etc shadow file on your Linux machine. My name is Michael Mullen, and let's get into it. So the things you're going to learn if you follow along with me today are, first off, you'll learn about the SHA512 Crypt algorithm usage inside of your Rust programs. This function is provided by the Rust crypto project, and you can find links to everything that I'm going to show you in the description below. I'm going to talk to you and you'll learn about the particulars about the etc shadow file format. You'll learn a little bit about reading files in Rust. You'll learn a little bit about Rust Rayon. You'll learn a little bit about the clap crate. And you'll learn a little bit about atomic variables. The agenda today. First off, I'm going to talk about some absolute basics around password hashing. I'll then go into a little bit of detail about the etc shadow file format. I'll talk to you about the usage of SHA512 Crypt by the shadow utils, which kind of reads and writes the shadow file. We'll talk about some cracking basics, and then we'll jump into the code. So what are the absolute basics? The absolute basics of password hashing is that all password hashing uses a salt. A salt. A salt is a number which is only used once, also known as a nonce. You use this salt for two reasons. A salt protects your users from each other if two users are using the same password. So if two users are using the same password and you hash those two passwords with two different salts, you will get a result, a key. You will get two different keys for those two different users, even though those users have the same password. The other reason, the other protection that using a salt gives you is that it protects from pre-generated rainbow tables. So in the past, when salts were not used, an attacker could generate giant tables of all potential passwords that he would want to try. And because there is no salt on these, so long as he got access to the resulting hash, he would not have to do the hash himself. He would just have to look up the password into the rainbow table and be able to figure out what the password is for the hash that he got just by looking up his rainbow table. So a salt will protect against that because rainbow tables can't have salts in them because they are completely randomized numbers. The other important thing to understand about password hashing is it's not just hashing the password, as in taking the password and passing it into SHA-256 or SHA-512 once. It is hashing many times. It's taking the password, it's taking the salt, and it's hashing those, and it's kind of jumbling them up and hashing them over and over and over and over and over again. Many iterations. OWASP and NIST have guidelines about how many iterations you should use as a minimum, and those two are different. I'll give links in the description about what those are. They differ between the amount of iterations you should use differs between 1,000 or many millions. And the kind of the rule of thumb that you should use is that use as many iterations as you can without giving your users a poor experience. What etc shadow uses by default is 5,000 iterations of the SHA-512 Crypt algorithm. So yeah, some more information about password hashing or password-based key derivation functions you can find in the NIST special publication numbered 800-132. And again, the link is in the description down below. So the shadow file. Let me show you a shadow file. So I have a shadow file here that I got from a previous from when I was working out how to give this presentation. I have this shadow file here. So as we take a look at it, you will see that there are many users on this system, but there is only 2 users with passwords. Everyone else has this exclamation or a star in it, meaning that you can't log into those users. The users that do have passwords are the MM user and the root user. So the file format for the Etsy shadow is it goes user, then it has a delimiter of a colon, that it has your hash data, another delimiter, and then it has a bunch of data that we don't really care about for cracking the hash password, but it's all about kind of when your password was last changed, when you're allowed to change it next, when you have to change it next, when you're going to be given a warning about, hey, you're going to have to change your password soon, and the expiry date of the user themselves. More than just the expiry of the password, but the expiry of the user account. We don't care about any of that. We only care about the user and the hashed data. So the hashed data is delimited by the $ symbol. And its format goes $algorithm used, $salt, the resulting hash of taking the salt and the password, and the result is that hash. For algorithm, the algorithm that is used on modern systems is now the SHA512 Crypt algorithm, and we see that in a $6. So as we look at the shadow password here, the shadow file, we have this $6, which means that this is using the SHA512 Crypt algorithm. Then we've got the salt contained here, and this is a base 64 representation of the binary data salt. And then we have the resulting hash, and again, this is a base 64 representation of the binary hash. This base 64 is a little bit different. The base 64 used by SHA512 Crypt is a little bit different from the crates.io crate called base 64. And I don't really understand the reason why it's a little bit different, but it is, and that's fine. We don't really have to worry about it right now. As you can see in the code, the Rust Crypto project takes care of that for us. So a little bit more about SHA512 Crypt. SHA512 Crypt is used in glibc in their crypt function, crypt CRYPT, in their crypt function since version 2.7, and we're now at version 2.35. Thus, it's used by the Shadow Utils package, which uses glibc. You can find the Rust Crypto implementation in the URL given, and again, that'll be in the description down below. Now, an important thing to understand about SHA512 Crypt is it would not pass, it does not meet the NIAP mobile device recommendations. And the reason why it doesn't meet those recommendations, because there is only a single recommendation for the NIAP mobile device recommendations, and that's PBKDF2 using an Hashmap of a SHA-2 hash algorithm. I will get more into detail about PBKDF2 in the next video. Specifically, the algorithm, what you need to use for your password derivations is FCS underscore COP 1.1 condition. You'll find the link down below about that. So this SHA512 crypt doesn't meet the recommendations that a lot of companies want to target when they are making secure devices. So for example, like smartphones and things like that, smartphones often want to become NIAP verified, and the smartphones cannot become NIAP verified if they use the SHA512 crypt algorithm. Now, of course, we don't really care about NIAP verification on your Linux hardware, your Linux operating system. So SHA512 crypt is good enough for us. Some of the arguments against using the SHA512 crypt are that the length of the password matters towards how many times the underlying hash algorithm is run. So in the case of doing the SHA512 crypt for the Etsy password file, we have 5,000 iterations per normal. However, we have additional iterations on top of that based on the length of the password. And that means that if you have a long password of, say, 64 characters long, you would actually be doing at least 4% more hashing than a short password. That means that it has two meanings for us. The first meaning is that if an attacker can kind of monitor how long your process is doing the hashing, it can determine the length of your password. Now, that doesn't really help an attacker all that much. It might, if a password is 64 characters long, that's a lot of, that's really hard to crack. So an attacker having that knowledge isn't really all that useful, but it is a piece of knowledge that is given to the attacker, and we want to limit as much information as we can to the attacker. So that is a minor issue. It's not an issue like in real life, but it is a potential, like, it's a mathematical issue. The second issue is a little bit more severe. So say you're running the password hashing algorithm on a low-powered device, and each hashing run takes up time. What this means is that if you have a long password, the longer your password is, the longer it takes to derive the key that your password derives down into, which means that on a low-powered device, say it's only got a single core, and it's a very low-powered core, which means it's going to take a very long time during the underlying hash algorithm. That core is being taken up. Its time is being taken up. Its resources are being taken up by the hashing algorithm. And more resources, more CPU resources are taken up by that hashing algorithm, which means that an attacker might find a way to do a denial of service attack upon your low-powered devices by just guessing bad passwords that are very, very long. So that's kind of another argument against using the SHA crypt algorithm. It could cause a DDoS attack upon your system. These really don't matter for us for when we're running like desktop Linux or Linux on a laptop. We've got a lot of power here. uh, 5,192 iterations isn't all that much more than 5,000 iterations. So it's SHA512 Crypt is good enough for our usages. But just keep in mind that if you're making a device that you want to be NIAP certified, you're not going to be able to use SHA512 Crypt. So let's talk about some cracking basics. There's two main ways of going about cracking passwords. There's doing a brute force attack, which is just trying all of the characters of all of the lengths that you want to potentially try out and feeding that into the hash algorithm with the given salt and seeing if that works. So what I mean by this is you'll first try to hash the password of A and see if that matches the key stored on disk. And if that fails, you will try B and then C. And you'll go through the alphabet and then you'll try AA, BB, AB, AC, all that, AAA, BBB, AAAA, BBBBB, AAC, AB, 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 CAAB, AB, you know, so on and so forth. You'll try all these different kind of nonsense passwords. And that's going to take a very, 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 very long time to do. Yeah, and that's just not going to work out for you. It's it's just not going to work. The other way in which you can attempt to crack passwords is hoping that your user has a bad password that is contained within a dictionary. So you get a big long list of potential passwords and you try all those out. And you can get these word lists from the internet based on, passwords that have been cracked in the past and have been put in this big long word list, or other types of word lists. If you're running Arch, you can find word lists from the AUR in a package called word lists, and that'll give you a whole bunch of different word lists that you can use for dictionary based attacks. So it's a big long list of words. Instead of just going A, B, 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 it'll go password 123, password 345, and it'll try a whole bunch of different, commonly used passwords, maybe semi less commonly used passwords, passwords that have been cracked in the past. So the password might have been good in the past, but it was cracked based on a bad algorithm, say 10 years ago. It's a good password, but you used MD5 on it, and therefore someone cracked that password. They put it in a list, and now that password is kind of bad forevermore. So yeah, when you're cracking passwords, parallelism is very good. And that's why all the real cracking utilities use the GPU for more parallelism. When you're on a GPU, you can crack, you can try and attempt, several thousand words at a time, rather than on my machine, because I have a 32 core machine, I can try 32 passwords at any one point in time using the Rayon crate. So Rayon for the win. It's going to help me out a lot, but a real password cracking utility would use the GPU. I'm not going to go into GPU programming because I haven't learned how to do that in Rust yet. So let's take a look at the code. There's one important thing that you need to know before we jump into the code. There's just one important function for the actual hashing, and that is the SHA512 _crypt _B64 function. What that is going to do is it's going to take the password, it's going to take a potential password, it's going to take the salt, it's going to take the number of iterations to run, and it will give us a base 64 encoded potential password that we can check against. Everything else that I'm going to show you in this code is either parsing the etc shadow file or doing some plumbing with clap arguments, or plumbing, hooking up Rayon, stuff like that. So let's get cracking, and let me show you the code. So here we are in the main function. This is the main function from the Crack Shadow program that I have hosted up on GitHub. The first thing that I'm going to do is I'm going to define some arguments using clap. This allows the user to optionally pass in the name of a file for the shadow and the name of the file for a word list. If the user gives us those values, we will use those values. But if not, we've got some default values. The default values will be either shadow, and that represents this file right here, or the default value for word list is contained within this this constant word list file here, and that's just this kind of really quick word list that I created while debugging, and you can see that it is very small. So once we've got those values, we're going to run the crack shadow function. So as I jump into the crack shadow function, the first two things that we do are we open up the shadow file. We read the contents of that file into a string, and then we turn that string into a vector of ref strs representing each line in the file. So for each line inside of shadow, we will have an entry inside of that shadow entries file. So for example, there will be a shadow entries file containing the data that I'm currently highlighting. We then do a very similar thing for the word list. We open up the word list, we read the contents of the word list into this string. We then break down that string into a vector of words based on the lines inside of the file and now inside of the string. So yeah, now we've got a kind of a list of words that we will be using to crack, and we have a list of entries into the Etsy Shadow file. So what we're going to do now is we're going to use this pariter function. Pariter is part of Rayon, and it comes from doing this Rayon prelude. So what this allows us to do is take a normally sequential iterative pattern and make it parallel. So what that means is that I am going to take, on my machine, which is 32 threads, I am going to take 32 entries out of this shadow entries list and start processing on them. The processing that I'm going to do is I'm going to do a filter map. So I'm going to take each line out of that, out of the shadow entries, and I'm going to parse it to try and get the user, the username, the salt, and the key out of that, that shadow file. So if we jump into that, you can see it's kind of some dirty parsing stuff based on the colon and the dollar symbol, that sort of stuff. I'm going to parse that out, and if I get a good entry, that means that I can try cracking that entry based on the word list. So we're going to search for a key. The search for a key, first of all, ignore this Atomicbool for right now. For each entry inside of the word list, again, we're going to use the pariter to do 32 iterations at any one period of time. And we're going to filter map on this to create a list of passwords that we found. That should trigger something in your brain going, what do you mean a list of passwords? We're only trying to crack one user's password. There is only one password for that user. Why are we creating a list? I'll get back to that in a second. So to build up this list of passwords, we're going to feed the password that we found in the word list, the word that we found in the word list, the salt that we got out of the shadow file, and the parameters, which just contains the iterations of 5,000 here. It's just saying run the iterations for the algorithm 5,000 times. And that will generate for us a base 64 encoded version of a potential key. So then we match that potential key to the key that we found in the shadow file. So again, the shadow file, we parsed out the username, the salt, and the actual key stored in the file. And when we do the search for the key, we are iterating over the word list and getting a potential key in base 64 format for each one of those words. If that key matches, if the key that is potential based on the word list matches the key that is found on disk, then we add that password to the list. Again, that should say, why are you making a list? The reason why I'm making a list is that when you're running an iterator, or specifically a Rayon parallel iterator, we're not running a normal for loop, and we thus cannot break out of our loop. Again, also, because we're doing we're running our code, what Rayon does is it runs our code on all of the different threads, the CPU threads available to it. Because it's doing parallel programming, you can't have mutable values inside of the work that you're doing. We can't have mutable values. We can't set this is the one key that we found unless we use a mutex. And I don't want to use a mutex because mutexes are heavy. Mutexes are heavy, and I would kind of lose a lot of the gains I get from parallelism by mutexing this stuff away. Kind of. Mutexes are heavy, so I don't want to use a mutex if I don't have to. So I'm just going to generate a list of passwords. Of course, the list will only contain one. So I don't want to do, so say my word list was 10,000 lines long. I don't want to do 10,000 iterations over that word list if I found the word on the third word in the list. That's why I'm using this Atomicbool. So if I find the word, I'm going to set my Atomicbool to true, and on each iteration before I do the hashing, I am going to check the Atomicbool. Atomicbools are fairly quick because they are a hardware provided concept. They are a hardware provided way of only allowing one thread to access the underlying Boolean at any one point in time. So it's kind of like a mutex, but it's hardware enabled mutex, and it's only for a very specific set of types. You can get an Atomicbool or an atomic U32 or an atomic U64, kind of the basic integer types, that sort of stuff. Like you don't have an atomic for a string. That doesn't exist. You would need to use a mutex for that sort of thing, and I don't want to use that heavy of a mutex. And that's why I'm building a list, but I'm preventing myself from iterating further using the atomic bool to say, if the atomic bool is set, don't bother running the hash again. Now, of course, I'm still iterating over the word list 100,000 times if my word list is 100,000 in length, but that's not really a big deal if I'm not doing any work with the word. And so I'm basically blocking doing work with the word if the atomic bool is set to true. So yeah, I've now got a list. Now the list only has one entry in it, but I've got a list of passwords. So once I have that list, I'm going to take the first item out of that list and pass it up to the user. Pass it up to the user of this search for key function. So let's go back to where we called the search for key. I am then going to use that value that I've gotten out of it to create another list, because don't forget, we're not just iterating over the word list, we're iterating over every value inside of the shadow file that we provided. So now I've got, using this map functionality, I have now got a hash map of usernames to passwords that I found by cracking them using the SHA512 Crypt B64 algorithm. So once I found those passwords, I then pass all of them out back to the main function. And I print them out. So let's give this a try. So first of all, I want to generate a new password. And of course, I don't want to do this on my real machine here, because not only do I not want to screw around with my password right now, but I don't want to crack my password and show that on the internet. So I'm going to use a virtual machine I use for development, and I'm going to make a fairly easy to crack password in that virtual machine, and we'll crack that password using the utility that I just showed to you. So I'm going to use my Alma Linux 9 virtual machine, and I'm going to get into super user and change the password for my user. And I'm going to take a password out of this password file that you cannot see because it's off screen, and it generates more drama that way. So I am then going to plug it into the passwd algorithm, which kind of calls all the shadow utilities. And now if I cat on Etsy Shadow, we will see that has a salt and a key. Hopefully it represents the password that I just set. And it does. Okay, so we've got this shadow file here, but I want to get this shadow file onto my main machine so I can crack it on my main machine. So let's copy. Let's get back into Sue and copy Etsy Shadow into my home directory. I then want to chown it. And I then want to chmod it to 600. All right, so now we can grab that. And it started with a 6LSP. 6LSP, so I've got the right file now. And let's run our program and try to crack the password. So it is important to run in release mode when you're doing this hashing stuff, because the hashing themselves take a very long, well, they take a very long it takes a long time in debug mode to run the hashing algorithm. And if you were to run this in debug mode, it would take, 10, 15 seconds to do to crack these passwords, when ain't nobody got time for that. So the binary that I'm going to be running is the crack shadow, and then I am going to give it one of these word lists that I got from the word list package on the AUR, the Arch user repository. So let's see if we can crack these passwords. So we actually found two passwords. We found MM's password, which is password with a capital P. I thought I was being pretty cool there using a capital P, but nope, no good. And my dot for my root user. So it cracked those from this. So this represented that, oops, I'm highlighting it incorrectly. This represented that capital P password. And this represented that dot. So I hope you have learned a lot about password hashing. I hope you've learned a lot about Rust Rayon, about reading files in Rust, about using atomics in Rust. And yeah, I hope you've learned a lot in this presentation. In the next episode, I'm going to be talking about PBKDF2 and Argon2. Like I said previously, this SHA512 crypt would not get validated as per NIAP. It would not meet NIAP recommendations, and therefore a device which used SHA512 crypt for the passwords would not be validated per their guidelines. So I'll talk about how we can create a shadow file using PBKDF2 and or Argon. But yeah, that's in the next episode. So I hope you have a good day. Thank you very much for watching.